How's it going? I hope you're all doing well, and I'm also happy to be with you to do this short presentation about FlowVision. As I've been introduced, I'm Daniel. I'll be representing this company, and today this is just going to be a short introduction to the FlowVision software complex and CFD in general. I know it's the end of the day, but I hope the coming hour will be interesting and informative for everyone. So let's begin. This is the topics that I hope to cover today. We'll be talking about CFD, and this is just the study of fluid dynamics, why it's important, what is the purpose of CFD packages. And then we'll have an overview of the CFD process from the point of view of an operator. Here we'll discuss all the steps that make up a CFD project, some difficulties that can be associated with it, and what FlowVision does to help you with them. Then an in-depth look into FlowVision itself. So this is its capabilities and what makes it such a powerful tool for solving your CFD applications. And finishing that, we'll just have a look at the many applications and the variety of CFD tasks that FlowVision can help you solve, where CFD is applied. Yes, this is going to be the section with the pretty pictures. And we'll, of course, do a nod to MIFI and make a separate note on the tools specific to solving the problems in the nuclear industry. I'd make a quick note right now that FlowVision does offer free trials for students. That's definitely something that you would want to check out if you're interested in learning more about this field, if you want to try hands-on to solve some of your own project. But I will be sharing more details about how to make use of this at the end. Also at the end, I'll be answering questions. These can be asked. I don't know if you have the chat enabled, but I'll be happy to take them at the end and answer the best I can. So first, a little bit about FlowVision, who we are. It's a Russian multi-purpose CFD software package, first created in the 90s for the aerospace industry. Now it's been expanding and providing services in the CFD field for over 20 years, during which it's grown, developed tremendously, and continues to do so. The primary purpose is to provide a tool to accurately model and solve computational tasks in modeling complex, multifunctional physics processes. So this is things like fluid flow, heat transfer, chemical reactions, kinematics, etc. And yeah, the aim is on the range and the variety of physical processes that you can model, the versatility of operation, simplicity, and modernization. In short, we want you to be able to solve any task using modern methods, technology, and keeping the interface easy to learn, easy to use. So the first section, I will start the lecture today with just discussing what fluid dynamics is and what CFD is. Why do we need it? I understand that you will have had a few complicated lectures today, going into the process and looking at what makes up. This isn't a theory course, so it's the end of the day. We won't go deep into all the maths. This is just to provide a surface overview of the fundamental concepts, provide structure, if you will. So let's begin. Fluid dynamics. What is fluid dynamics? Like fundamentally, what is it? Well, the complexity and the depth of the definition will, of course, vary depending on who you ask. But at its core, pretty much in the name. We're studying the motion of fluids. Fluids, of course, can be anything, liquids or gases, anything that moves. And as a field, this area of study is surprisingly old. So I know many think of fluid dynamics as something modern. You imagine planes, you imagine rockets. But honestly, this picture that you see on the slide, the big one, that's not just squiggles. So it's not somebody checking that their pen works. These are observations and notes from the diary of Leonardo da Vinci. So he was walking around Italian towns, looking at channels, and these are the first observations of turbulence, you know, as you do. But the point is that the concept of fluid mechanics goes a long way back. So, I mean, it's kind of crazy to imagine. So it's the 16th century, and even much earlier, there's already people in the world who are looking at the air, looking at the water, and they're like, I'm going to count that. And this gives birth to the analytical approach. Essentially, analytical modeling, clever people make observations, sketches, think about it a whole lot, and come up with equations that describe what they see. And that's great and all, but how do we know that they're right? How do we know that this analytical approach is correct? Well, the obvious answer is we just test it. And this is going to be our experimental approach. We make a 2-scale experimental model, see if our analytical results work in real life. And these models can be absolutely huge. So the picture that you see, that's a massive wind tunnel that NASA has at the Ames facility in California. And it's really gigantic. It's 80 feet by 120 feet. If you're not on American units, then this is about the size of an 8-story house, 8-story building. So these are massive. And sometimes even that isn't big enough. So there are research labs in places like Colorado, Bolivia salt plains, where they actually use the geography of the Earth to test these experiments and test these hypotheses. And as impressive as everything is, you can imagine that it's probably very expensive and pretty complicated to set up. So, okay, what if we're not NASA? What if we can't afford to make an entire plane every time that we want to test something? Well, most of us can't. This is where CFD comes in. And note that all we've done is added another word, computational, because guess what? Now we're doing the same thing, but we're using a computer. And the process here is going to be broken up into 3 basic steps: modeling, discretization, and iteration. So the modeling stage, this is what we get from all those analytical studies, you know, all that maths that those clever people were doing. Yeah, these are essentially just a formula that describe how the fluid behaves. So how it changes in mass, in momentum, in energy. What else is affecting it? Heat, chemical processes, radiation maybe. And the key equation that fluid dynamics is built in this one, the Navier-Stokes. I believe that you probably will have seen a lot of it today. And I know that first time I saw it, I was pretty taken aback. It's a pretty scary thing. I mean, what is that? Is that triangles in there? But the point is, it's very difficult to solve. It's not an easy thing to solve, and yet that's what we're trying to solve. But we can't solve that analytically. You're not going to be able to do this on paper, not for any real case anyway. At least I've never seen anyone do it for a real case. So what we can, however, do is at best solve these simple cases like Poiseuille flow. And Poiseuille flow is essentially a fancy way of saying we have a slow laminar flow within a channel. It's predictable, it moves slowly, it's symmetrical. Yeah, we can consider that and we can model it. And from here, we have this idea that, okay, maybe I can't solve this whole big equation by itself, but I can apply it to something really simple. What's really simple? I mean, a cube is simple. So we can solve much simpler equations on simpler geometry, like cubes, and apply them to that. But unfortunately, how does this help us in real world applications? I mean, unfortunately, not everything around us is a cube. But what if it was? What if it was just cubes? So the idea here is that we take our complicated real world model and we break it up into lots and lots and lots of these cubes. And now instead of those scary Navier-Stokes equation, we can have a lot of simple equations that we just have to count for every single cube many, many times. And you know what's really good at counting the same thing over and over again? Pretty much computers. So these are the steps of discretization, in short, just making something continuous into countable objects, and iteration, counting over these cells. Of course, the better your computer, the more it can count, the bigger and the better the model that we can build. And with the explosion of computer development and with computing power, the accuracy and complexity of CFD software also improves. And here's how we get to modern CFD packages like FlowVision. But what's even the point? I mean, yeah, calculating things all well and good. Pretty pictures aside, why should anyone be interested? Why should industry invest in this? Well, there are actually many reasons, and they will all depend on the product that you're making. But here are some general ones. Quicker and cheaper design process. It's much easier to make a model on your computer, which you can always tweak, retest, alter a little bit, rather than make 10 physical prototypes. Again, building a plane every time we want to test it, kind of expensive. Then we can study systems where controlled experiments aren't really that great. So the system may be too big, too complex, too dangerous. Maybe it's even impossible to study it otherwise. So for example, think of climate change. That's a hot topic. We can't exactly make a scale model of a hurricane and then unleash it on a city to study structural damage, although that would be pretty cool, but somehow I don't think you can do it. And even if you could, I don't think people would be too happy about that. So yeah, we do it on a computer. And lastly, the level of detail that you can analyze your model in is pretty much unbounded. In a real experiment, you would have to formulate it very carefully, plan it immaculately, advanced sensor technology, and these are all problems that CFD overcomes. Did you forget to measure something? No problem, do it afterwards. Want to look at something in more detail? No problem, just enhance it. And pretty much the more complicated a project, the more vital CFD becomes because these reasons come together. Imagine a nuclear power station, you have those material and construction costs, the time it takes to build it, fees for regulations, all of that only to find out that something doesn't work. Yeah, conclusion, spend that money on a CFD team instead. And this is where stuff like FlowVision comes in. FlowVision, all it is a tool set, it's the workshop, the bread and butter of such applications. And like any workshop, the more different tools you have available, the more freedom you have in what you can create and how you can apply it. So for CFD software, these tools can be very different. Which physical phenomena can it model? How accurately? How much freedom do you have when collecting these results? How quickly and reliably can you perform calculation? FlowVision is a multi-purpose package, and this means it has a variety of these tools. It means it can be used to a great effect in academia, in industry, wide range of applications at any level. You can use it at home, you can use it on a single computer, or for massive, gigantic models on clusters, supercomputers. The aim is simply to provide you, the user, with as many options as possible to solve your tasks, regardless of the scale, difficulty, or the application. So now let's touch quickly on what makes a CFD package. There's many CFD packages, but what are they? What do they consist of? Fundamentally, at its very simplest, a CFD code consists of two parts. So there'll be a preprocessor. This is where the user describes the problem, the environment, to the software. So this is your geometry, what processes you're solving, the fluids that are present, external conditions, internal features, so on and so forth. And then there will be a solver part, which is a programmed code that takes all of the inputs that you've given it, and this actually performs a calculation. Great. Let's note two things. Firstly, as you can imagine, the preprocessor, its only function is that you can enter data in such a way that the solver can accept it. And for a lot of super specialized solver codes that you can find in universities, for example, this can look like just a big text file, or maybe a directory system of text files that you have to dig around through. The point being, the software can have an unnecessarily steep learning curve because of how it's set up. It's not user-friendly. FlowVision, of course, provides a neat user interface. Everything is collected in one place. Everything is laid out. You can view the geometry, conditions you've applied, all in a logical order. You don't have to go looking for it, which makes it more intuitive, makes it easier to learn, easier to work with. The second thing to note, for specialized programs, at its core, this is all that they need to provide, a preprocessor and a solver. But they're kind of missing something. I mean, a post-processor. What's the point of the calculation if you can't see the results or do anything with them, right? So you need somewhere to view and interact with the results, and there are various specialized software just for this purpose. In FlowVision, makes it even simpler. This is combined with the preprocessor, meaning that you have your task formulation and your results all in one place. And this now is beginning to look like a full-fledged CFD program, where within one interface, you can set up a project, solve it, and view your results, all neatly laid out. But FlowVision has a modular structure, and this allows it to go much further beyond that and provide a range of other tools to enhance your capabilities. These are mostly focused on managing projects, automating processes, creating your own user modules, interacting with other software and more. It provides way more than just the necessities, and we will discover the powerful implications of this in greater depth in a little bit. So now we've got our definitions in order. We have a rough understanding of what CFD is, why we need it, what makes a CFD package. Let's now have a brief overlook of what that actually looks like to use a CFD software to solve a task. What steps does it involve? Here we have a brief outline of the process that you go through to make a model. Again, we're not going to be diving too deep into the theory. Again, this is just going to be end of the day, surface overview, just to get you thinking about the steps, what needs to be considered, the challenges that may be involved. And going from here, again, a quick mention, 2 things to keep in mind. First, each of these steps can be analyzed in endless detail. Like we can have an entire course dedicated to just each step alone. This is a lot of stuff. Secondly, going back to the workshop analogy, the end result depends on both the tools available and on the person using them. So for any CFD problem that you go through, this will be a process regardless of what you use, what you're solving, and you do really need to have an understanding of how it works. The value of FlowVision, our aim is to simply provide you with the widest spectrum of tools available and to make it easy to actually use them. But we do need an understanding of the process. So let's begin. First, we need to understand the model. Before you even start your project, understand what it is you're trying to model. And abstraction is key here. It's going to be absolutely crazy to model the entire galaxy. Find your area of interest, focus on that. So for example, if you're interested in the processes inside a nuclear reactor, like you wouldn't model the whole station. I mean, you wouldn't model the cafeteria and the parking lots because why? It's useless. It's too much. So similarly here, it's a good practice to make a list of the environment conditions, what you're modeling, what data you're trying to collect. Try to know as much as you can beforehand. And honestly, I can't stress this enough. It's really good practice to get into. I mean, I wasn't in university that long ago. I remember being like, writing on paper, who even has time for that? Trust me, it's better to do this. And once we've done that, it's time to build our model geometry. We create our geometry, we make it in a CAD program of our choice, import it into the CFD package. FlowVision tries to make this easy for you. We work with a wide range of file types. We take it from a range of sources. And typically, a key consideration with geometry is accuracy. How accurate is your geometry model? FlowVision isn't afraid to take complicated or non-standard geometry due to its really advanced meshing systems. Again, we'll talk about this in a short while, but basically what this means for you is that as a user, you would never have to simplify or modify your geometry at its core to make sure that the program complies with it. Here's what I mean. From the point of view of a computer, your ideal geometry, again, boxes everywhere. It would be blocky, all perfectly aligned with the mesh. And of course, the real world just doesn't look like that. It just doesn't. So still, when we create accurate geometry, this is a strain on the computer. Some programs you need to take care with, for example, sharp corners, tight curves on a small radius, tiny gaps, moving objects. FlowVision gets rid of the headache entirely. No, just build your model the way you need it, whichever software package is comfortable for you, import it as it is. Next, we need to define our boundary conditions. This is, we've basically at this stage imported our beautiful geometry into the program, and we need to formulate the conditions. So this is that modeling stage, remember, where we describe the environment to the program. we need to think about boundary conditions. As you recall, we're not modeling the entire world. We're selecting a region of interest, and that's going to be our computational domain. So computation domain, fancy way of saying that's what we're solving. And like in the picture, if we have this gas pipeline, we're not going to model however many kilometers of it. We're going to take a section, because pretty much on a grand scale, it's all the same. And we can see the whole picture. We can see that it's just a section of a long pipeline, but the computer can't. And so basically, we're just going to need to tell the computer what's happening at the boundaries. Where does the flow enter? Where does it leave? At what velocity, pressure, temperature? What are the walls like? Next, we're going to need to know what's happening inside the domain. What substances are present? Water, air, what do we have? What is it that we're modeling? Is it just motion? Is that all we care about? Or are we also interested in, for example, thermal effects, radiation, maybe mixing processes? All of these things will depend on the task that you're modeling. What about the flow? Is it turbulent? Is it laminar? If turbulent, then how are you modeling that turbulence? These are all things that you have to think about. You have to think about, but FlowVision aims to hold your hand through it. You have a large selection of models and boundary conditions to choose from. And that way, simply select whatever is appropriate. The method is going to be best suited to the needs of your task. And it's all intuitively gathered in the same place. Nice. Next, our discretization stage. As you recall, after the modeling stage, we mesh it, where we're breaking up our model into many blocks. And meshing is a very complicated procedure, theoretically. Why? What makes it so difficult? It's basically you have to answer the question of just how many blocks, how many of these boxes am I splitting my model into? And that's really hard to say. Your challenge is, your task here is to accurately capture the geometry and the flow features. So for example, if you have a region of turbulence or the high gradients, this is going to affect the flow. This is the behavior of the flow that I want to capture. I want to capture that effect as well as possible. And let's say, I don't know, I have an eddy or swirl, and my cell, my box, is much bigger than that eddy. Well, I've just lost that feature. It's not going to show up in my results. And that's because we're calculating the averages over the whole cell. And if in the worst case scenario, I have one cell for my entire model, I wouldn't see anything. I would just get flow in, flow out, nothing in the middle. And this we can see on this diagram on the left. On the top, if you see flow over a bench, just goes straight past. It doesn't even realize that that step is there. And as we refine and make more and more boxes, we begin to see that we have swirling patterns. We have circulation going on there up until we get to kind of a ridiculous cell count. So again, here's our question. Why not just use a lot of cells? Just make as many as possible. That way we're guaranteed to capture everything. And yeah, that's very true, but you're going to have two considerations. One, kind of useless, and two, it's going to take a very long time to solve. And this is because, if you recall, in the iteration stage, we're performing these calculations for all of the cells. So the more cells we have, the more calculations we need to do. So it's going to take a longer time. In the CFD world, time is money. Like literally time is money. Like I know it's a phrase, but here it really does apply. Why? Because you have processing power. If you're renting servers, server rent time, project time, and we can be talking a difference of days and maybe even weeks here. So you want to capture the flow as accurately as possible while using the least amount of cells possible. And of course, nothing is ever ideal. So you're going to be looking for a balance in the two. So let's address those problems. Let's avoid having lots of cells in regions that don't need it. One thing that we can do is mesh in two stages. This is what FlowVision does. We have an initial mesh. This is where you're going to be splitting the domain into equal blocks of volumes. These are all equal boxes. This can sometimes be called a box mesh. I wonder why. And we call it an initial grid. Again, FlowVision speeds up this process by generating this mesh automatically, dependent on your user specification. The second stage we have is the refinement stage. Here we're going to be splitting the cells into smaller cells, only in the regions of interest to capture the geometry and the flow features. So notice here how more or less it's all the same, but next to the walls, we've got finer mesh resolution. Again, FlowVision will adapt automatically to the specifications that you feed it. Another thing that we can do is address the time to speed up the process. Let's just solve it faster. We have a better computer, we have more processing power, faster counting, pretty straightforward in that sense. But the idea here is that we can imagine this model, like 1 million cells or more. And by the time you finish counting that on one local computer, that's it. Like your week has gone by a lot of times just so long. So the idea here is, hey, why not split this into many little pieces and give many computers a little piece of the model, and then they can count it all together. Teamwork, nice. Note here, though, that we're splitting the mesh not by volume. So it's not something that we can just, roughly divide up into equal parts. And this is because we've refined features. So some parts of the model, they will have more cells than others. And we want to distribute it in roughly the same amount of cells so that every computer is counting roughly with the same intensity. Otherwise, well, that just wouldn't be fair. And again, FlowVision will do the split automatically for you. And finally, all of that done, we've specified the problem, we've discretized our model, we're finally into the calculation stage. We made it, we're solving it. This is the part where the computer is counting. You don't have to do anything. And this is usually until your solution breaks and you absolutely have to do something. And this is because solvers are very complex. They're fussy. They're sensitive to the formulation that you've put in. All of the choices and all of the decisions that you've made up to this moment, they will affect how well the solver reacts to the problem and the accuracy of the solution that comes out. The first period of working with any CFD code is pretty much trying to find where you've done something wrong, and it's always operator error rather than solver error. FlowVision tries to remove as much of this pain as possible by making a really robust solver. We focus on robustness. This is stability at various velocity. We go from stationary flows all the way to hypersonic, which is Mach 5. There's a variety of methods for the solver to interact with the mesh. We use a finite volume method. This is this FVM. This is industry standard. Most solvers are going to be using this. And again, all of our selections, implicit method, conservative methods, is all to ensure that you have a stable and a fast calculation. And lastly, of course, we're doing post-processing. If you recall, we don't need to do it on a third-party software. You can view your results within FlowVision itself. We provide a lot of visualization tools that are highly customizable. You can set them up exactly how you need them. You can monitor and display distributions of any variables, even with the ability to specify your own variables within the program interface. This is all within the program interface. You can create animations. And yeah, that's nice to have because, only thing that's better than pretty pictures is pretty videos, I guess. And yeah, remember FlowVision's modular structure? The viewer module will allow you to view your results remotely, even by other people, even if they don't have the software license. So basically, you can share the results of your creations with whoever you want, show everyone. It'll be amazing. And another cool thing is that you can view these results as the project is being solved, step by step. Again, cool. You can monitor your solution taking place. And now this whole process that we've just described, that we've gone over, is to some basic extent going to be achieved by any respectable CFD program. This is where we're going to be talking about FlowVision's strengths and the capabilities that will help you model even the most complicated of tasks, simplify your working processes, and yeah, again, reiterating, our aim, reduce the time spent on setting up the project, get the user to the calculation and to the results faster. This is just going to be a demonstration of how far you can really go with FlowVision. First, let's start with this. Regardless of what color belt you are in CFD mastery, there's going to be something of interest for you. So for beginners, as mentioned before, intuitive interface, everything collected in one place, laid out in a logical order. Don't waste your time learning to navigate many different programs and interfaces. Spend that time instead getting comfortable with the concepts of CFD and getting real results. And we provide dozens of tutorials that will walk you through a variety of projects, help you get an idea of the different models and processes and what they do. For experienced, intermediate, and advanced, maybe CFD veterans, you will find that the program is constantly evolving, constantly modernizing. We incorporate new models for solving a whole spectrum, whole variety of tasks. So if you're used to solving a particular kind of task, FlowVision aims to provide the tools to complete it easier and faster. Sometimes you can even automate it to some extent. If you have a very specific task that you need to solve, you can even extend the program beyond its basic functionality through the numerical engineering platform, which we will absolutely mention in just a short while. And for all users of FlowVision, we provide an up-to-date detailed documentation where we explain in detail everything that's in the program, so you don't be confused. An active technical support service that is always happy to assist. And we even have a cool blog that discusses, various CFD concepts, how to get the most out of FlowVision functionality. So do check it out. It's very educational, if I do say so myself. Next, touching on the modular structure in more detail. Different program parts that communicate through an agent. What does this achieve? What's the benefit? Firstly, it's the ease of working on a network of several machines. So you can have your project open on a local machine, set calculations running elsewhere entirely. We make this process extremely quick, extremely easy. This speeds up your calculation. This allows you to work with several projects simultaneously. So yeah, get more done quicker. Also very nice. A viewer module that we've kind of talked about already, to quickly access and interact with the results, even without a license. So you can share your work with others. You can monitor the calculation progress remotely. And building on that, FlowVision, there are other modules that will help mostly in managing your project. So automating launch processes, even queuing runs, or you can extend functionality by linking with third-party software like Abacus, Nastran, things like that. Handling geometry. FlowVision is really strong in this regard. We accept geometry in range of CAD and FEA formats. So this will be SolidWorks, CADIA, Autodesk Star, Abacus, Nastran, whatever you're comfortable with. Create your model in that, whatever you prefer. Easy import into FlowVision. We even import entire assemblies. Simple geometries like tunnels, pipes, boxes, all of that stuff that will consist of basic shapes, cubes, cylinders. Don't even need to build it elsewhere. You can create it within FlowVision directly without the need to ever even open a CAD package. We also accept data not just from CAD. You can have real-world scanned objects, for example, laser optical scans. On this picture here, model of a skater that's created with motion capture technology. That's pretty cool, I think. And accuracy. FlowVision, reiterating, we're not afraid to deal with complicated or non-standard geometry. What this means, never simplify it. Just build it as accurately as you need it, import it into FlowVision, let it handle the rest. And if you need to perform some kind of manipulation, so for example, maybe scaling, maybe a translation, rotation, whatever, you don't have to recreate and re-import the geometry. Instead, just easily do it within the program. You won't lose any of your progress. Next, another focus of ours is to save resources, reduce the load on computational resources. We reduce the time that it takes to get your results. Here, we try to help you, first of all, by making it easy to set up a two-dimensional case. So this is useful for quickly running tests, conducting mesh convergence studies. If you recall, when we refine or we adapt a cell, we're splitting it effectively into 8 parts. So that's 2 in each dimension. And this is why in some places, if you set up your initial grid so that the domain is just one cell, you're still going to lose this property as soon as you refine it, because in the region of refinement, it's going to be 2 cells or more. With FlowVision, setting up a true 2-dimensional case is as simple as just specifying the dimension that you want to exclude, and you greatly increase the speed of your calculation. Another thing is that frequently you can exploit lines of symmetry. So we model half an object if it's symmetrical, save half the computational resources. With FlowVision, we're going to be taking it a step further by having periodic boundary conditions which allow you to identify repeating elements. They can be linear or they can be sectors, and we can model just one of these elements, again, greatly reducing the computational resources required. The strong meshing capabilities. FlowVision reduces the time spent on meshing by automating as much of the process as possible. That way, you spend less time setting up your project. Another thing here is where we can look at the subgrid resolution system. This means that we can capture your geometry as accurately as you've modeled it. Have a look at the diagram in the side of the slide. So here we have an oval, and a curved surface, usually meshes don't deal that well with curved surfaces. If you look at the traditional meshing, this is what's called snapping to an object surface. And you can see that, yeah, it's kind of captured the dimension, but it's not round. You've basically discretized it even further by making a bunch of sharp edges. Another thing other software will use is by cutting out the cell to fit it best. Again, you have these sharp, jagged edges. This doesn't even really look like that oval. With subgrid resolution, have a look at the bottom picture. This is what FlowVision uses. We have full, accurate geometry capture. Again, to simplify the process for you, we're going to be automating as much of it as possible. For the initial grid, you specify the cell count, the cell size, maybe some control points to affect cell density. The software will automatically generate the mesh based on those parameters. So have a look at this complex assembly. So here, what do we have? Regions of various interest to us, regions of varying geometric intricacy. This would just be a nightmare to do manually. You would not want to build this mesh manually. Takes too much time. FlowVision does this quickly. Similarly with adaptations and grid refinement, you can specify regions to be refined by selecting objects, selecting boundary conditions, or you can apply the refinement in a fixed volume, or maybe to occur based on the results of the calculation. Again, whatever you feed FlowVision, FlowVision will automatically adapt the mesh based on the conditions that you're specifying. And FlowVision makes it extremely easy to utilize moving bodies. We've lost a guy. That's a guy jumping into a swimming pool, in case anyone's interested. We implement Eulerian mesh methods. All that basically means, don't worry about the complicated terminology. All it means is that objects aren't physically fixed to the computational mesh. And this makes it easy to create models with motion in 6 degrees of freedom. You can even have full surface contact just because this object is free to move along the mesh however we do. This movement completely based on user definitions, maybe fluid forces that act in it, so things like inertia. And another cool thing, a cool freedom that we give you is that geometries can even completely leave or re-enter the computational domain. So you're not bounded in any way in that regard. Automatic mesh adaptation. Now this is actually really cool. So again, we have moving bodies. We don't know beforehand how our solution is going to look. And we know that mesh refinement can be assigned to regions around objects, or maybe to occur by condition. What this means is that the mesh will dynamically change throughout the simulation. Here in this visual example, we have a lid detaching from some manner of airborne capsule. Do you see how the refinement follows the object? What this means for you as a user, you don't have to guess what the solution is going to look like. You don't have to guess the motion trajectory. You don't have to guess a volume that you have to refine beforehand. Let FlowVision do it automatically over the course of the calculation. And to save computational resources, again, excess refinement, if you look left behind in its wake, merges back into the initial size because we're no longer interested in that region. Fluid surface interactions. This is a very important thing. Again, complicated terminology. All it means is basically the deformation of a physical structure with response to internal or external flow. So here we can see pressure forces acting on the satellite dish and deforming its surface. Why this is important is because fluids can cause oscillations. Some of you may be familiar with the Tacoma Narrows Bridge accident in the 40s. That's kind of the textbook example of how structures can fail if you don't consider the effects of fluids acting upon them. Another thing, aircraft wings, turbine blades, that can break pretty easy if you don't consider fluid forces. FlowVision can do that. It couples with FEA software pretty easily. We have a linker agent to do it. Another thing, internal flows, very widely used in medicine. So a heart is kind of a textbook example as well. You have blood vessels acting as kind of compliant tubes that change size dynamically. So this is with response to the changes in like blood pressure, flow of blood velocity. Why this is important, again, let's look at this. Here we don't have anything breaking, but if you don't take this into account, you're going to overestimate the wall shear stress and kind of significantly. And this is especially key when modeling things like aneurysms. So incorrect modeling will lead to somebody getting unnecessary invasive surgery for something they don't even need. And yeah, that's not pleasant, I shouldn't imagine. FlowVision has a clearance and gap model, and this is really one of the more unique features. It provides fast and accurate solutions to problems where you have, for example, ultra fine clearances. So we can work down to, I think, 1 micron in the computational domain. This is especially applicable in, I don't know, like screw compressors, gear applications. These can be dynamic or static. The gap model is able to account for surface roughness and asperities. So this is crucial in calculation of, say, leakage, maybe oil wetting, things like that. Again, all the user needs to do to apply this, you perform your initial meshing as usual, and then just enable the gap model. That's all you need to do. Specify the threshold for clearances and count it in the calculation, enable the model, and that's it. FlowVision will then automatically identify the necessary cells and apply modified governing equation to those areas. This helps you retain full accuracy of your solution with pretty much no increase to the workflow or to the calculation time. Multiphase interactions, again, can model interaction of multiple phases, gaseous and liquid, can model a variety of processes like phase transition, phase interaction, particle motion, so when it's disturbed by external forces. Here we can see lubrication of gears. So the gear is spinning, rotary motion, it entrains the fluid and sprays it all over the place. And we can track the motion of the fluid particles. Similarly, fuel injections, responsive to vibrations and car movements, to sloshing, things like that. And hybrid parallelization. So naturally, we have MPI threading technology. This allows you to solve really large projects. So if you have, say, I don't know, a project of many million cells, you can solve it on machine clusters, supercomputers, so on. And again, parallelization and distribution of resources performed and managed automatically. You don't need that headache. Numerical engineering platform is a fairly new introduction into the FlowVision complex, introduced, I believe, in 2019, so a couple of years back. And this is a really cool new feature that I'm excited to tell you about. What this is a software platform to develop, implement, and even sell engineering software and its components to simulate complex interdisciplinary processes. Who is this intended for? Pretty much anybody who needs that little boost to the FlowVision functionality. So researchers, developers, niche manufacturing. So for example, maybe you need super extra levels of precision. Maybe you have a really super specialized niche interdisciplinary task that combines a lot of advanced processes. I mean, yeah, that's really hard, but if there's a really niche demand, it's very unlikely that major vendors will be able to prioritize development for this functionality. So what you can do is you can build off of the available program framework and extend its functionality to suit your needs. So you can make things like new mathematical models, methods of unifying various software for interdisciplinary problems. You can solve field-specific problems using FlowVision as kind of a core, like the root, the trunk that you're holding on to. And furthermore, another cool thing is that this platform acts as a marketplace. So many of these extensions, they would require a huge amount of work to turn it into a standalone marketable product. But say you created something really cool and you want to share it with someone, make a buck off of it, you can commercialize these creations by selling them not as standalone products, but as extensions to a common platform that's readily available. So yeah, we got to it. Our applications. This is going to be the area with all the pictures. We'll do an overview of some different fields, different industries where CFD is in demand, and some choice projects that have been completed in FlowVision to demonstrate the versatility of the program. So where do we encounter CFD? Not going to lie, pretty much everywhere. You can have a little challenge. Try to find something that doesn't interact with gas or liquid somehow. I don't think you're going to get a very big list. The obvious one, of course, transport, automotive, rail, aerospace, marine. These all continue to be major recruiters in the field. I don't think that comes as a surprise to anyone. Then we have our built environment. So construction, energy, even electronics. So this is stuff like ventilation, heat transfer, energy process, all that. But there are two major fields that are rapidly growing in opportunities where CFD is now developing very quickly, and this is environmental and biomedical. Both should be kind of self-explanatory. Climate change is a pretty hot topic that I think many of you might have modules on. And so there's new interest in modeling pollutant effects, weather prediction, coastal defenses, or things like that. With biomedical, with advances in computational powers, we can do blood CFD. So we model anatomy, drug delivery mechanisms, all of that good stuff. For a more in-depth look in the automotive industry, where might we see and what might we use in FlowVision? Here's an example with aquaplaning of a tire. If anyone here has driven during heavy rain, you'll kind of know the importance of tread depth. So the treads need to remove the water from the road so that the tire doesn't lose contact. Otherwise, you're going to get aquaplaning. So basically, you have a layer of water between the tire and the road surface, and your car turns into a big glorified sled. Here we can see the modeling of water displacement, the thin layer that gets trapped and trained, and the effect on the whole vehicle motion can all be modeled in FlowVision. Lubricant dynamics. So here we have lubrication of a differential. We have a full assembly that's been imported into FlowVision, rotating components. We're going to be using the gap model on the gear teeth. So that's all these small spaces that are dynamically changing. And again, to top it all off, again, multiphase interaction. So in many CFD programs, this kind of geometry and motion, honestly, that would be a nightmare. In FlowVision, this very much is a matter of just ticking the right boxes. That's it. Sloshing, we've briefly discussed this already, but I like this video, so we can have a look at this again. Fluid injected into the component, under external forces to the model thrown around the domain, we can model this particle motion. Medicine. Oh, did I miss a slide? No, I didn't miss a slide. So we have a complex hard model. This considers things like the electromechanical properties of muscle tissue, the dynamic action of the valves into the heart chambers that move more fluid. So we've discussed this as complex FSI modeling, as the tissue deforms to accommodate the blood pumping through the organ. We can use it in sports. Again, this man doesn't want to jump into the pool, but he is jumping into a swimming pool, good for him. But what we would see is, let's note firstly, how accurately this body geometry has been captured. So it's not blocky, it's you can even see the detail on the fingers. And I guess without the video, you're gonna have to trust me that the fluid motion, the motion of the object, of the man, is very fluid. Also, there'll be water displacement. So when the man jumps into the pool, we're going to have a splash when the body crosses the boundary between the two phases. And yeah, flow around a manipulator, standard flow around an object, but again, demonstrating that this object is capable of complicated movement. We can visualize the flow vectors. This is in all 6 degrees of freedom. Electronics, this is mainly to do with cooling of components and preventing the damage from overheating. We have a variety of thermal modeling methods. We've discussed that FlowVision has robust mechanisms for modeling, for example, conjugate heat transfer. Same with other heat transfer processes. Natural forced convection, when air moves over the surface. You can model heat sinks and sources within the domain. Passive or active cooling, which essentially just means, do you have a fan or not? And you can, again, import the assemblies. You can import assemblies of varying complexity with many intersecting bodies, contacting bodies. You can resolve thin clearances down to literally microns. And again, we can model the thermal resistance between components. How do we do this? We basically create small surface offsets between the regions, move them slightly apart, and then use that gap model, that clearance model, to simulate thermal resistance, simulate bridging. And of course, there'll be interest in other industries. Here we have a cool video of a reusable launcher module from a rocket booster that's making a water landing. Again, we have all these phase interactions as both from the brake jets when it's first approaching, but also when the object crosses the phase boundary and drops from the air into the water. On the other image, we have maritime applications, modeling a hull's interaction with the water surface, can incorporate wave models, exploit the line of symmetry to solve the project accordingly. So, you know, cut out half of the model, save half of the mesh. In short, to summarize this section, FlowVision has the ability to tackle projects for any application. And with that in mind, let's look closer at what FlowVision has specifically for the nuclear industry. Here we'll be drawing attention to some very advanced specialized capabilities and describe some nuclear projects to show how the program has adapted to the tasks. Tools that are specially for nuclear is special turbulence models, integration with third-party codes like Tort software, and we can look at this in more details. So for conventional media, so think air, water, heat conduction is only really important near walls and solid surfaces. And you can experience this when you go outside. So if it's a really hot day and you touch metal slide, I don't know, a piece of playground equipment, you might burn your hand, but you don't burn your hand if you just have it next to it. That's because the heat conduction really only relevant very close to surfaces. But if we have liquid metals, however, this is going to be kind of different. So the heat conduction becomes roughly of the same order for the entire flow. Therefore, the heat transfer mechanism is going to be very different, and so is the behavior of the flow. Therefore, we have special models that account for turbulent heat transfer by counting the turbulent Prandtl number. So this is basically the ratio of your flow momentum to the thermal diffusivity. And in nuclear applications, this isn't constant, this changes. So we account for that change with this model. And as you can see by the graph, this is just vastly improved performance and calculation results. You have a far lower relative error margin, especially higher Pecklet numbers, completely blows a standard turbulence model out of the water. Similar, we've done some interesting experiments with RANs, with Reynolds averaged Navier-Stokes. Typically, this is frowned upon because RANs is kind of considered that, you know, intricate flow features can kind of be smoothed over, can be lost. But here we conducted an experiment where we mixed some streams at different temperatures, and we received a very low relative error, so of magnitude of less than 1%. And essentially what this shows is that in FlowVision, with a well-constructed mesh, URANs can yield extremely accurate results. So there shouldn't be a worry about it. Periodic conditions, again, saving our computational resources. And even for complicated nuclear applications, we can have axisymmetric elements like the fuel rods, which we can model with the periodic boundary condition. So don't model the entire thing, conserve your computing power, save your time. Tort integration, Tort TD. This will be familiar to you if you're working in the nuclear industry. What it is: three-dimensional discrete ordinates neutron transport. First time I heard this in university told me absolutely nothing. Essentially, specialized code that is used in the industry to assess safety of light water reactors, gas-cooled reactors, can model movements of individual control rods, can model movements of banks of control rods. Pretty much what it does is calculates neutron flux from radiation emitters and distributions of radioactive isotopes. And yeah, these can come from wherever. These can come from particles on the system boundaries, so entering or leaving the fluid. This could come internally within the computational domain, or it can be generated as an interaction of materials present within the system. FlowVision can export and receive data directly, working linked with Tort. Significantly simplifies work with this code, and the code is really important for these applications. So let's look at some case study scenarios. Here you can see modeled a bypass valve. Again, just an excuse for me to put in more cool pictures. The bypass valve contains a sphere. The sphere we're modeling as a moving object, and the motion is going to be dependent on the processor forces. So pressure drops, the sphere settles in the valve, closes the channel, nothing goes through, the pressure rises again, and this displaces the sphere back upwards, which allows the flow to come through. On the right, again, heat transfer modeling in a reactor. We've discussed that FlowVision is good with a variety of heat transfer models. It does conjugate heat modeling very well. What I draw your attention to here is that this is a large model that contains many small channels. This can be solved in a supercomputer, and this is just what the results of such a project would look like. Here, again, more heat transfer modeling. Again, we have a reactor with tiny channels that conduct the fluid flow. But here, look, we've built on it. We're exploiting the axisymmetrical nature of the geometry to model just a sector of it. So we only took a quarter. Again, saves our time, saves our resources. And yeah, we can use FlowVision to model pretty much any kind of heat exchanger which are present in all energy applications, not just nuclear. For example, here we have a specific case with optimization. So this project models an oil-cooled transformer. I don't know if you're familiar with how this works, but here's a brief description. We're using natural convection to cool components. Natural convection meaning we're not blowing, using mechanical elements to blow flow across the surfaces. We don't have fans or anything. It's just pressure gradients that result in moving the flow. As the core and the windings heat up, the temperature in the tank rises. This is going to be heating the oil, and it's going to cause the oil to move upwards to the upper portion of the tank. There it begins to dissipate the heat, being cooled by air out to its surroundings. And as it does that, it cools down, begins to flow back down, and re-enters at the bottom of the tank. So far, so good. Basic heat transfer problem. We've seen a bunch of these in this presentation. But in this problem, the focus is optimization. Where do those channels, you know, those channels that move the oil up and down, what's the best location for them? How are we going to be designing this? Like, what's the ideal place to put them? And essentially, what we need to do to get this is to run pretty much the same project over and over and over again, just changing the location of the tubes. Again, easily done by connecting with a third-party optimization software. It helps us to some extent automate the process and to plot the results, as you can see in this graph, hassle-free to the operator, to the user. That would be you. And yeah, today we've had a look at some of these applications. We've discussed what CFD modeling is. And I'd like to draw attention that if this was interesting to you, I'm hoping I've left you with a good idea and impression of what FlowVision is and what it does. And we do have a student trial version available. You can get a license for free for a period of 2 months to solve your problems. All of the details you can find on our website. There's a form. Only note being, if you're a Russian speaker, do please use the Russian version of the website. That'll be flowvision.ru, not flowvisioncfd.com. The rest of you, please check out flowvisioncfd.com. And if you're interested, we will be in touch. Just fill out the form. A quick note on those of you who are joining us tomorrow. We will be doing hands-on practical work. In the morning, there will be a session with a tutorial case to get you familiar with the program interface, to let you play around, see what it is. And this is going to be run by me. Later on, there will be 2 more sessions where you can create and run a project modeling fuel rods. Those sessions will be led by my colleague, Natalia. And yeah, if you're joining us tomorrow, make sure that you do have FlowVision installed and working on your machines. And yeah, that's me done. To everyone present, thank you very much for listening. Right now, I'm available to answer any questions that you may have.